Welcome everybody to the Diels-Alder lab. Here's the outline for what I'll be going over in this video. I'm going to talk about the reaction and some of the conditions which are pretty specific for this reaction. Then I'll talk about purifying the product and go over the hot filtration technique. Then some concepts about melting points, and in the end I'll show you the actual experiment. So here's a look at the reaction that we'll be doing. It's a cycloaddition reaction using butadiene and maleic anhydride to form this cyclohexene anhydride product. Here's a look at the most basic reaction or mechanism for a Diels-Alder reaction. We have our diene that attacks a pi bond, which we call the dienophile. Now, if we take a look at the frontier molecular orbitals for the diene, we don't see a classic pi and pi star configuration like we see for the dienophile. Since there are 4 p orbitals that are in conjugation with each other, there are 4 molecular orbitals that they form. The first one being pi 1, where all of them are in phase with each other, ranging up to pi 4, where they are all out of phase with each other, and we see 3 nodes, and that's why it's the highest in energy. There are 4 pi electrons in this conjugated system, so they will fill the pi 1 and pi 2 orbitals, meaning that pi 2 will be the HOMO and pi 3 will be the LUMO. The HOMO of the diene will then attack the LUMO of the dienophile, and there needs to be in-phase overlap between the frontier orbitals as shown here. The 1,3-butadiene used in this reaction is a gas at room temperature, which makes it difficult to measure and handle, so we'll actually be making it in situ using 3-sulfolene as the reagent. And we can confirm that this reaction is happening by testing the pH. Sulfur dioxide is released in this reverse Diels-Alder type reaction, and as it reacts with oxygen and water, it'll eventually turn into sulfuric acid, which we can then pick up on a pH strip. So we can test the vapors coming off of the reaction by placing a pH paper moistened with some distilled water between the drying tube and the water condenser in the apparatus, and it'll start turning a reddish pink, indicating the presence of an acid. This helps confirm that 1,3-butadiene is being formed to react with the maleic anhydride. To reach the activation energy for this reaction, we're going to be using xylene as the solvent because the reaction happens around the boiling point of xylene. But we need to be careful not to get it too hot, because if we boil off too much xylene, the reaction vessel will heat up, and that'll create contamination, where the product actually starts to decompose into a dicarboxylic acid instead of an anhydride, as shown here in the table. So the anhydride product that we want is shown here on the left, but we can see the dicarboxylic acid contamination if we allow it to get too hot. We can monitor this by checking the color of the solution. We are wanting to see a light brown color, kind of like a cream soda, meaning that some contamination has formed, but if it gets too dark of a brown, that means the majority of our product has been decomposed and we would need to start over. Once the reaction is complete, we'll let the product crystallize out of the xylene solution, and we'll be adding some toluene to help with this process. And then we'll gather the crude product using vacuum filtration and recrystallize it using Lagrogne. And this is where we can separate the diacid contamination, if it was present, using the hot filtration technique, which I'll show in a second. But the reason that it does work is because the diacid is not soluble in Lagrogne, whereas the product is. Here I'll be showing some diagrams on how that technique works. So we've got a hot water bath with 2 test tubes, one containing the Lagrogne solvent and the other with the crude product that might have some diacid contamination with it as well. Once we start adding the Lagrogne, the crude product will begin to dissolve into that solvent, but the diacid contamination, being insoluble in Lagrogne, will stay at the bottom as a solid. From here, we can take a piece of cotton and put it in the test tube just on top of the contamination, then using a Pasteur pipette, start transferring the Lagrogne solution into a new clean test tube. The cotton will prevent the contamination from moving with the solution into the pipette, leaving the crude product dissolved in Lagrogne by itself, and then we can continue the recrystallization process like normal from here. Now, all of this should be done in a hot water bath to ensure that the crude product remains dissolved in that Lagrogne solution. If we did this at room temperature, we would risk some of the crude product coming out of solution and being left behind with the diacid contamination in the cotton. Once we have the purified crystals, we can characterize the product by taking a melting point and running an IR spec. Now, just briefly, I want to go over some concepts around melting points. For example, let's say we're taking the melting point for the anhydride product, which we would expect to see around 104 degrees Celsius. But let's say that we were not able to remove all of the dicarboxylic acid, which has a melting point of 174 degrees. So in the crystal structure that we're measuring, it contains the majority of the anhydride product, but has some acid contamination. And the question is, what's going to happen to its melting point if the contamination actually has a higher melting point than the product itself? To answer that, let's take a look at this diagram, which shows us two compounds and their respective melting points. So compound A melts at this arbitrary temperature, and compound B melts at a higher temperature than compound A. Now, if we look at M here, it's representing a mixture between compounds A and B, where the crystal structure they are melting is 80% compound A and 20% compound B. And if we look at the melting point for that mixture, it is actually lower than that of the pure compound A. And this all has to do with how well the crystal structure can form for each compound. If you have a pure crystal structure where it's formed of all just one molecule that each have the same shape and size, then they can fit together really tightly and well, and that forms a nice crystal structure, kind of like this nice brick wall shown here. But if you have an impure crystal structure where we have different molecules with different sizes and shapes, they don't fit really well together, and that weakens the crystal itself, and that lowers the melting point as well. So when we have an impure compound, we're going to have a lower melting point, and that's why recrystallization, a slow recrystallization, is important. Because if a compound recrystallizes too quickly, those impurities will be trapped within that crystal structure. I'll start by adding all of the reagents. So I'll measure about 260 milligrams of 3-sulfolene and add that to a 3 milliliter conical vial with a large spin vane. Then I can weigh out 130 milligrams of the maleic anhydride, which was a little clumpy, so it was kind of hard to get out, but I eventually got there. And then I can add that to the conical vial as well. Then lastly, I'll add 200 microliters of xylene to the conical vial and start setting up the apparatus. But before adding the drying tube, I'll moisten a pH paper with some distilled water and place it in the water condenser like this so that I can test the pH of the vapors. And now I'll just let this reflux for 30 minutes, making sure to monitor the reaction so that the color doesn't get too dark of a brown, but remains a light brown color. If we check the pH strip, we see a red-pink color, meaning that there's an acid present, which is a good sign that the 1,3-butadiene is being formed. And this light brown color is also a good sign that the reaction is happening, so things are looking good right now. After the half hour has passed, I'll move the apparatus off of the heat so things can cool, and I'll be adding 250 microliters of toluene to help the product crystallize out of solution. I'll stir the solution with a spatula and scratch the sides of the glass just to help with this crystallization process. And finally, I'll place it in an ice bath to make sure that all of the crystals did come out of solution. Then the crystals can be isolated using a Hirsch funnel and vacuum filtration. Then I'll be using some cold Lagrogne to rinse the contents of the conical vial and also rinse the product on the Hirsch funnel, and I'll go ahead and rinse it a couple times. Once the crude product is dry, I'll remove it from the Hirsch funnel and then move it to a Craig tube where we can start the recrystallization process. I'll be using Lagrogne again, this time as the recrystallization solvent, so I'll go ahead and add that to the hot water bath as well. And now I'll start trying to dissolve the crude product by adding hot Lagroine and stirring it with a spatula. But after adding quite a bit of Lagroine, you can tell that the solid is still not dissolved, meaning that there's probably quite a bit of diacid contamination. So from here, I'll be doing the hot filtration technique. I'll add a piece of cotton on top of the remaining solid and allow the solution to settle a little bit. And once it has, I'll start pipetting the solution through the cotton and transferring it to a new test tube, which should keep the acid contamination behind, hopefully leaving just the product in the Lagroine solution. I'll check that the product can come out of solution in an ice bath, which is looking like it definitely can. So I'll transfer it back to the Craig tube in a hot water bath so that we can continue the recrystallization process. And the product can still come out of solution in the Craig tube, so I'll redissolve it in a hot water bath and this time leave it at room temperature so the product can recrystallize slowly. Once that's done, I'll scrape the sides a little bit just to break up the crystals, and then use a stopper and a propylene test tube once again to remove the liquid from those crystals, and I'll centrifuge it just for a few minutes. Now I'll weigh out the crystals so we can calculate a percent yield. The empty watch glass is about 9.736 grams, and the product only made it jump up to 9.741 grams. So I didn't isolate very much, but let's characterize it to see how pure it is. I'll take a melting point starting a few degrees lower just in case there is contamination, but it looks like the solid starts melting around 102.4 and finishes around 103.5 degrees Celsius. So there probably is some contamination in there, and we can check for that on the IR now. I'll add what little product I have to the salt plates and then use the neutral mold technique to run the IR spec since it is a solid product. And there it is. There is definitely some diacid contamination in there. We can see the carboxylic acid funnel and an additional carbonyl peak around 1698 it looks like. But we do see the two carbonyl peaks for the anhydride around 1840 and 1774. And that, along with the melting point, does indicate that the product was produced and was the major component of the crystals isolated.